This has happened in this case, this has happened there, okay? And then there is this final question. I mean, we have automated the questioning. We have automated the thinking. Now, can we automate the judgment? Probably not. If anybody has an idea how to do this, I will be very happy to know about that. But I really don't know how to let the computer decide whether this theory that was proposed by the computer is interesting or not, okay? And the problem is not that the theory is not bad. The theory explains things. It's the question of whether it's interesting or not. And the question of whether it's interesting or not has more to do with me or with people than with the physics, okay? This is something that we don't really know what it means to have an interesting theory. We don't know what is. I like to put this not from the point of view of interest, but from the point of view of beauty. We need beautiful theories. It's not something that is supposed to have been said by Einstein. If he didn't say it, he should have, because his theories were beautiful, okay? And this is something that we have to decide. We can decide by ourselves if we are interested in knowing the answer. Otherwise, probably there is a way of letting the computer follow this cycle until it converges into something. But it might not interest us at all, okay? We might not want to know about it. I mean, what do you care, okay? But if we want to decide whether this explanation is interesting or not, it's something that we have to decide by ourselves. So in this first part of the scientific cycle, okay, I think that the role of people will start to decay for a while, okay? The computer can do it faster than us, okay? Here, I think we are still important, probably not because of the physics, but because of us, okay? That is a danger. I put a danger signal there because up to now, I mean, I told you in the discussion of the first day, my interest is in the inhuman part of artificial intelligence. Okay, what can the computer tell us that we cannot tell? I mean, anything that I did here could be done by any of you in much less time than a year ago, because it's fairly easy. Okay, but I'm interested in the part that was not clear. I like the dipoles because they were not predicted. I mean, I didn't know about it, or I had forgotten about them. Okay, and this came out of this, and by just breaking the cycle here with me, that is a danger signal. It's a signal that might spoil the whole exercise. Okay. This, by the way, this is what I call Monte Carlo science. Okay, it's basically of doing science by searching, and maybe genetic science. I don't know, but essentially searching randomly. Okay, and this is not the first time it has been tried. I mean, this has been essentially what you need for this is to have a way of exploring the universe which is fast enough that you can afford it, okay? And the first people that were able to do this were the biochemists, okay? And they do this routinely. The first paper that had in the name robo-scientist, it was this paper in like 10 years ago, okay? And it was this machine, and it was called ADAM, of course, okay? And apparently what this it was design drugs, okay? They were designing proteins to be good for some particular sickness or something. They were trying to solve something, okay? And essentially because the biologists by then knew how to play with DNA and knew how to create DNA and then transform that DNA into proteins, they were able to, I mean, this thing was able to stay in the room trying new things for a long time, and apparently found something, okay? Found enough for them to build another bigger machine some years later that was obviously called Eve, okay? And that apparently is still working. I saw a paper recently in which not only, I mean, these papers came from a lab in Scotland, okay? the paper that I read was from a company in California. They were not only doing this to design something, the machine was reading the literature for hints, okay? Was reading the literature, understanding the literature, find which possible molecules were going to be good for cystic fibrosis or something like that, and then designing this randomly, okay? So this is something that has been done already, and it's industrial right now, okay? This I told you that I was going to tell you something about channel. This is a paper that is still in archive from the Carlos III, okay? And it was done by Flores and Pastor. Basically, they are doing a channel. I told you, causation is the science of control. They are trying to control the drug in a channel, okay? And basically, they are doing the same thing. They have the channel, they have a channel, the flow is going this way, and then near one of the walls, they have a volume force in which they either push up or put down, okay? For a short period and for a small volume, okay? Do it at random and then try to find which are the places in which this thing is doing something good, okay? So they just do many experiments and then collect all the places in which the drug is decreasing, and then look which are the characteristics of those places, of these pieces of the flow. And they find things that usually in these things which are still quite primitive, they are not earth-shaking, but they are interesting. Essentially says if you're pushing up, okay, you want to push up in a place where this is the wall and the flow is coming this way, okay, and this is the wall normal velocity. Blue is negative, so you want to push up when the wall normal velocity is negative. That makes sense, okay. That also means that when the wall normal velocity is negative, it goes to the wall, the stream wave velocity is high. You're in a high velocity streak. That also makes sense. You want to do that in a place in which the pressure at the wall is high. That makes sense, but it's not obvious. I mean, it's something, to me, it also is in the level of a minor discovery, okay? For pulling down is the opposite. There is something interesting here. It doesn't really make a difference whether you push up or you pull down. You have to push up or pull down in the right place, but there is always a right place. Okay, so these are things which are already happening, and I think that they're going to be happening more and more. Okay. Now, why should we do this? I mean, I told you there is the possibility that this leaves you without a job. So why should we do this now? I mean, why should we work to train a computer to kick us out of our job? Well, because I think that we should, okay? And we should for this reason, okay? Remember, this is one of the slides that I used in the first day, and I told you this is a theory of the regeneration cycle of turbulence in a channel, okay? And this was a burst, and this happened in time, and this came from this structure that I had extracted from the flow, from the real flow. This is a good theory. It's a perfectly good theory. Even it's a theory that was done in collaboration between people and computers. They couldn't have been done without computers, okay? And it is a good theory because I told you, I mean, it takes 8% of the volume of the channel and it displays 60% of the drag. Okay, so why should we try to do something better? Well, that's the night sky. Okay, you know that you can make theories about the night sky, and people have been doing theories about the night sky for a long time. This is one of the theories. Again, this does Orion. Okay. This is the hunter. It was put in there for some reason by some titan that was unhappy with him. Okay, and apparently people like these things enough to use them for something. Okay, and some of these constellations, which make no sense. I mean, these constellations are not there. I mean, it's a chance alignment of stars which are in different places of the universe. They just happen to be together seen from the Earth, and at this moment, I mean, they will not be there in in 10 years, 10,000 years from now, okay? Probably this star apparently is not going to be there at all, and it's going to explode. That's what they tell now, okay? But there are these 12 constellations which are supposed to be important. This is the zodiac. People do predictions based on that. They have been using these predictions to decide the outcomes of battles. Should I go into battle now? Yes, because the moon is in the 7th house, okay, and blah, 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 okay? And that things work. It works 50% of the time, okay? Which is not that much better, that much worse than the 60%. So, you see something like this, okay? You say, well, okay, it explains 60% of the drug. Where is the other 40%? Are we missing something? Because we know fluid mechanics, and because we have been trained to see turbulence like this, are we missing something? We are certainly missing 40%. Are we missing something that we could have found otherwise? Okay, can we use the computer to do this better? Okay. The thing is, okay, we are very smart. People are very smart. Okay. But we are really prejudiced. Something that bothers me about my students, something that bothers me about me, is that we know too much fluid mechanics. We're doing fluid mechanics, which is something that we know. We certainly know what do we want to find it, and we find it, okay? So which is maybe good, maybe bad, okay? The computer is not as smart as us, at least not yet, okay? But it has completely different prejudice. I'm not saying that the computer is completely unprejudiced. The computer has completely different prejudice from us. Okay, so it's another guy. It's the extraterrestrial in the room. This is the thing that I think that we should explore. Okay, and we should explore it because of this. When you think of what is the scientific method doing, is optimizing knowledge. Okay, we are optimizing knowledge. There is this knowledge landscape in terms of some parameters, which are, whatever it is, one theory, another theory there. We observe, explain, test, and we are always going up to the top of this bump in there, that maximum, which is the paradigm, is the current paradigm of turbulence, okay, the current paradigms or whatever. Of course, it could be like that, okay? There could be a much better thing going in there, okay? And for that, I think that we should rely on something that doesn't know fluid mechanics, okay? And almost by definition, a smart guy who knows the Navier-Stokes equation but doesn't know fluid mechanics is a computer. So, okay, so this is my talk today. I'm happy to take. Oh no, yes. Well, okay, this is a summary, but this is. It's basically the same thing, but seen from the point of view of what the computers are doing. When for your problem of interest, the computers will take something of the order of 3 months or time, okay? What you get is data. When they are faster, you get answers. When they are trivial, you get questions, okay? And now I think that I can thank you. Thank you. I realize now that nobody was interrupting me, so if you have questions.
So when listening to you, you think about replacement. So you have some data here, or you can have a list of possible observation, and you have a list of possible theories on the other side. And to some extent, the computer nothing more shifts. So essentially, he can do a processing of the data, which is defined by the researcher. So there's never really a replacement. And when you are talking about your heuristic loop, the problem with a heuristic loop is you start with some data, you explain, and you get a theory, compute consequences, and so on. So every time you make one loop, essentially your game changes, your question changes, and it's not, I would argue, it's not a well-defined problem. So I would say that what machine learning can do is it can solve optimization problems. So what Steve was outlining. So once you have a well-defined optimization problem, so what is the best control for my drag or for my lift? What is my most accurate model which can predict the next configurations and so on? So all the optimization problems can be solved by machine learning. But at the moment we start to think about theories and understanding, it's something very subjective.
Well, no, okay. I mean, there's something. Okay, there's things which are subjective, and that's the problem I tell you here. Okay.